Two very difficult problems in computer science. One is distribution, so networking issues, and the second one is security, proving that something is working correctly. We are at the intersection of these two problems, actually. We are dealing with distributed system, and we need a high level of security for it.
And finding good names.
Yeah, that's the hardest part.
That's the hardest part.
That's the hardest part, finding a good catchy name.
Well, they're all Greek, so
that are not taken already. Right? It's like, the question is, what is innovation, right? And innovation, or what is innovation about? It's probably about producing artifacts. They increase the confidence into what is proposed will eventually run in production. Hey Nicol, how are you? Nice to see you.
Hi guys. Hi. Sandra.
I know. Nice to see you.
Nice to see you.
I'm Nicol. I'm from France. I joined IO 2 years ago. Before that, I was working in a research transfer organization in Luxembourg for more than 15 years. I'm the current director of software architecture in IO, which means that I have another look on all the pieces of software that we are building in IO. And I'm working closely with the architect to design these pieces of software and to help them solve their issues on a daily basis. What we are discussing today is the relationship between research, innovation, and implementation. The biggest part of our work comes from research, the idea of identifying a problem and try to find a new way to address it and to provide good stuff for the Cardano community. Usually what you are doing is basically paired review research results, which means that results that are validated by the community. And from there, we need to assess whether or not these research results are viable when we are looking at the Cardano ecosystem. Obviously, we could try to jump straight forward to implementation, but that's very risky because many of these ideas won't apply in the real world. So what we are doing is basically having this innovation layer in between, which try to bridge the gap, try to see if an idea is viable and makes sense. And then, if it is the case, moving to the implementation phase. And the whole goal of innovation is actually try to first, again, see if it flies, and second, provide enough evidence and enough guidance for the implementation team to be able to build stuff on top of that.
I'm Christian Barrecha. I'm a cryptography and blockchain researcher and lecturer, and I'm the Director of Research Strategy and Planning at Input Output. So as part of my role, I conduct research in cryptography and blockchain systems with topics that are centered around improving the Cardano ecosystem, but also advance the industry or the technology as a whole. And as a director in the department, I kind of ensure that the company strategy aligns with the research streams we are following, spark new endeavors whenever needed, and overview the progress. And this with the intention that we stay innovative, we stay proactive, and invest our time in the most promising way. Well, it doesn't start with research, really. It starts kind of with a problem statement, because building secure systems is a pretty hard task. So it's like you have to assess the requirements, like the security and decentralization, efficiency, and these are to some extent also contradicting requirements. So we have to figure out, where are we now and what's the problem we're trying to solve first. And for this, of course, and then you said it very nicely, then it starts with research, because more often than not, we cannot just take an off-the-shelf component if you're doing innovation. Right? It just doesn't exist yet. If you're lucky, someone else tackled the question, and we can start maybe from a research paper that exists, improve it. But often we also have to start from scratch. So we just go to the whiteboard and try to do, try to achieve something.
Be creative. Come up with something that nobody has thought of before. My name is Sandro. I'm a research fellow at IOG. I develop new protocols for blockchains, maybe to make them more secure or to increase the throughput or to reduce the settlement time, generally to make things more scalable. I'm originally from Switzerland. I did my PhD at ETH Zurich, and then I went to New York for a postdoc, and after that I joined IOG. Actually, just about the thing from before, so as a non-software engineer, like for me, there are 3 different levels of writing software. It's like Microsoft Word type of software, where it has to work, and then maybe software that is like security related, so you have to defend against an evil entity. Whereas Microsoft Word, there's nobody really attacking Microsoft Word.
Visual basic.
Right. Right. So you get my point.
Yeah, of course. Yeah.
And then, we're doing yet another, even more challenging thing, right? We're building a distributed system.
I'm Arnaud Bailly. I'm French. I've been working at IO for a bit over 3 years now, mostly as a lead architect for various projects. And various projects are mostly in the area of scaling Cardano, which is a broad area. So first, Hydra. I started the Hydra project with my other 2 colleagues at the time. Then Mithril, which is now also thriving. And more recently, so since the end of last year, I've joined the Innovation Streams projects at IO, and I'm really focusing on one of the innovation stream, which is about the Peras protocol. I'm also here the lead architect, but it's a very small team, and we are really trying to bridge the gap between the research and implementation, and try to shorten the life cycle, the time it takes to get from a research idea, which is good in theory, to an implementable specification and prototype.
What's interesting and challenging in the work we're doing, and what makes the interactions complicated? I mean, there are contradicting requirements, but there are also this kind of tension between the problems that are challenging and interesting from a scientific point of view, and that are expanding the knowledge, and the question of whether or not you can do X, Y, Z, and whether or not there are algorithms that can do that, and then the practical problem that people are trying to solve with Cardano, and that's something that's trying to solve the tension, because Cardano right now, there are really this problem. The problem of scaling Cardano is really challenging, because you want to scale a global network which is decentralized and distributed, as you mentioned, Sandro, and this is not trivial, because everybody, I think, one of the examples that's always flying around when we speak about blockchain and comparing with the real system is like, oh, but Visa or MasterCard, they are like doing 500 or 1,000 transactions per second, right? And they are doing that at a global scale. I say, yeah, of course, that's true, but there is only one Visa server. Or actually, there is a data center, of course. And that's really different from what we're trying to do, because there is this whole idea behind blockchain, which is quite important, which is this decentralized. And I think the whole decentralization scheme makes the thing probably 1 or 2 degrees.
And the upgradability feature, right? You cannot just push an update like Visa could. Yeah. So it really has to be secure, like right from the beginning when you ship it. It has to be secure. There must be evidence that it's secure, that we trust in the security. There must be a transparent process that showcases why we are confident, and this evidence must be understood by the community.
Yeah, especially with these blockchains and anything that is can be broken, because once you break your blockchain, I mean, there are some exceptions, but of course, if something goes terribly wrong, then it's gone. Like the whole idea of distribution of power is gone, because you're going to have to come together and decide how to fix it, right? So there are some famous examples of blockchains that they go down, and
we don't drop names,
and then people have to come together and decide how to fix it.
But there's usually 2 very difficult problems in computer science. One is distribution, so networking issues, and the second one is security, proving that something is working correctly. And the problem is that we are at the intersection of these 2 problems. Actually, we are dealing with distributed system, and we need a high level of security for it.
And finding good names.
Yeah, that's the hardest part.
That's the hardest part.
That's the hardest part, finding a good catchy name.
Well, they're all Greek, so
that are not taken already. It's like,
I guess the idea today is also to give some example about how we shape the relationship between research, innovation, and implementation. I think we have taken the example of Peras to discuss about it. First, Christian, do you want to tell us a bit about what Peras is?
So when we look at blockchain systems, right, one of the main features is transaction settlement. And often in many applications, you would like to happen that this happens fast, so low, small confirmation times.
The day before the coffee gets cold. So.
Yeah, exactly. Yeah, payment should send before the coffee gets cold. Yes, and now when we look at several designs of blockchain systems, there is this kind of the Nakamoto-style blockchains. They're very robust. They turned out to be very robust, but they also tend to settle a bit slower, right? You have to wait, and it's the probability that the transaction fails. It's kind of decreasing the more blocks is appended to the chain. And of course, the settlement time. So it's an interesting question whether with that design, staying in this space, with the we're secure in this dynamic participation model, can we still boost security? So can we break this apparent barrier that you really need to wait for quite some time to have your transaction settled? Or is there somehow an overlay structure we could impose that just could boost settlement times and make it then so you have a confirmed transactions in much less time?
Yeah, maybe to give a little more context, there are ways to get faster finality. You can do BFT-style protocols, and the difference between those and sort of Ouroboros, which aims to be a protocol that is going to be in use for a very long time, is that these BFT-type protocols, they don't have a property called self-healing. So the Ouroboros is designed to be resilient against an attacker that controls less than 50% of the stake, and even if that is violated, or even if the adversary at some point has a majority of stake in the system, if that ever goes back to normal, because say some honest guys were offline and they come back into the system, then Ouroboros can heal, right? So it can go back to a mode of to operating normally. And the BFT type protocols don't have this property, and that's why kind of Cardano wants to stick to Ouroboros, and as Christian said, see if we can find a way to improve the settlement time.
And self-healing is really critical, I think, because so when you are in this dynamic world that parties can join and leave, or their system is not always up. You also have these periods where participation might drop just temporarily, and if you're in bad luck, right, it's the people that currently are unavailable are many of the ones that support the system, which then leaves the adversary in this maturity state of he's probably currently controlling most of the active stake until the honest parties they reconfigure, they are back online, and at that point you don't need external kind of
for consensus.
For consensus, you just want that the system knows how to self-heal.
And I think it's very interesting to relate that problem also from a practical standpoint, what it means, because I think personally as an engineer, it really helped me to relate. When you look at a protocol in a paper, in a research, it's often very abstract, and you have all these questions about probability settlement. But I think in practice, getting faster settlement in the context of Cardano is also it's something that has a direct impact on users, because now if you're a user and you're making a transaction, and even if you're making a simple payment or a large payment, now if the transaction can be considered settled in a matter of minutes, or in a matter of hours, or in a matter of days, it makes a huge difference. And it also makes a huge difference in terms of risk. And to get back to the analogy with the central banking system, settlements in the current financial system is guaranteed by banks and ultimately guaranteed by the states, right? Here we have to do with the fact that there is no central body that will guarantee settlement. Yeah. So if you are making a transaction, if I make a transaction on the blockchain with Nicolas, if I buy a bicycle from Nicolas and I give him ADAS and do a transaction on Cardano, then Well, if my transaction is a fraud, or if I fake it, or if I double spend, like which is always you all think, but I got Nicolas' bike, then
there's no one to call.
There is no one to call back, right? There is no central authority to appeal to. If you are, and I guess everybody has had that experience, that you are buying something online, and then at some point you get on your somebody is getting your credit card number and is using it to do some payment at the other side of the planet, and then you get a debit on your account, and you can call your bank and you can say, hey, no, I mean, this is not me. And then, of course, if you provide some evidence, they will just roll it back. And actually, banks have insurance for that.
Yeah.
We don't have that, right? And
it's part of the business model that
that's
something can go wrong.
Yeah. And so it's very interesting to how did that impact people, and what are the trade-offs? I think that's an important part also of the interaction we have in the research in the research and engineering and transferring through the innovation stream is, and especially in the case of scaling never comes for free. So how does faster settlement translate into the more constraints or more resources you need to get in the real world, and what are the trade-offs, and how these trade-offs can be accepted
And one nice thing of this is evidence-based approach that we are following is exactly these trade-offs you mentioned, right? In research, we often then take the problem statement and say, okay, what are the assumptions we can assume? What can we assume? Like can we assume a good network? Do we have honest majority and this and that, right? And there are many cryptographic assumptions we want to make. And once you build up this model and you describe kind of what did we abstract out of kind of reality, because modeling everything is kind of impossible. So you have to kind of focus on the most important details. You have to document this because other people have to understand your thought process. And then you are able to formalize, hey, these 3 requirements that we would like to have, or these 2, or whatever requirements you would like, or whatever your goal your system should achieve. These are contradicting. We have to find a trade-off. So it's not black and white. It's just like some systems focus then more on 2 out of 4, or that's just the famous trade-offs we face, and we can formally. So once there is a model, you can actually theoretically also understand that there must be a limit, and so we don't try to chase the unachievable. We understand the space. That's why modeling in the beginning is very important, to understand where are the limits.
And that's interesting, actually, that you say that the model necessarily has to simplify the reality, because basically a huge part of what we are doing in innovation is basically to start to put more and more reality into the original design, to be sure that when we are introducing this external element and external constraints that are part of a real piece of software, then the properties that you have depicted in a research paper still make sense and are still relevant for what we are doing. And actually, usually it comes also with other kind of trade-offs that are kept aside at the paper level, and that becomes more relevant when we are trying to address what you have built and create a real system.
I think that's why we have these readiness levels, the software readiness levels. They kind of reflect this, we start at the drawing board. We always want to provide evidence, so we always have to document it such that other people can understand. So,
In fact, there's also the case that sometimes when you try to make more concrete the assumptions that we make in our papers, you discover new research problems that are actually interesting for us. One example is that the papers that describe for example, the Ouroboros protocol, they assume that the network it's a very simplified network model. So you put a block or actually an entire chain in at one interface, and then there's a fixed time bound that
he loves it.
You can see that it pains him, but so the idea is that everything gets delivered within a fixed time bound delta, the famous delta, and then of course this is not the case in reality. And in fact, it turns out that you can't just create a super nice consensus protocol and then run it on top of a network model that doesn't exist. You can't just create a consensus layer that's secure against an adversary, but then the network layer that's supposed to be implemented by the same nodes that run the consensus, you cannot ignore the attacker there. So we recently wrote a paper that actually formally looked into proving security also for the networking layer.
But I think you also encounter a similar kind of issue with the initial design of Peras, actually. And I mean, there was this issue about the certificate size and the amount of certificate that has to transit through the network in the initial version of Peras. And that's something actually that also shows value of the innovation process, because while Arno was working with his team on the prototyping of Peras, it's one of the first issues they had when they had to build the prototype. And basically, we circle back on research.
I think it's even before the prototyping.
Oh,
and that's where it becomes interesting in terms of the whole process and how the various parts tie together, and what we are really trying to achieve and what we are trying to find, because a prototype is already something quite involved. You have to code a prototype, and even if the protocol, I mean, Peras is a relatively simple protocol. At least it was. Right now, it's becoming a bit more complicated, but compared to other protocols, it's reasonably simple, and but still writing a protocol that's convincing enough. You know, it's just like. I would say that the analogy we can really we can pull in there, like you are a sculptor, and when you're a sculptor, if you are like Rodin, which is a famous French sculptor, and we all know the famous sculpture from Rodin, which are in bronze. But the problem is that, I mean, Rodin didn't carve the mold and then put the bronze in and the bronze came out. That doesn't work that way. Mm-hmm. Rodin did a few models, and the models were in plaster. And he did maybe some of them with clay and some parts and whatever. And then at some point, the thing became clearer and clearer to him. And then there was this, and you have like all the famous painters, all the famous sculptors from Rodin. It's exactly the same thing. They're trying to find the right model. And in the case of the case you are alluding at, Nicolas, it's really this idea that trying to find, rather than finding a prototype, which would be more time consuming, and especially if you want to simulate a whole network, trying to simulate or analytically or somehow analytically find a model of the whole network and the behavior across the network. And that's where we had this methodology that was also some papers that were published around it called Delta Q. And the idea of Delta Q is really, and that's one of the tools we pulled in there to try to understand the behavior of some parts of the protocol at large without even having to build a prototype, which would be time consuming.
But that's a very good point, actually. The whole process is about trying to fail as fast as possible. I mean, success is great. I mean, I would be very happy if we move from research to implementation without any issue and without any need to go back to one step earlier. The thing is that in many cases, you face some implementation issue, some design issue, and you need to address them. And the sooner you address them, the less expensive it is for everybody. Usually. I mean, having this kind of issue in production will be a disaster. Trying to address it through the implementation is expensive. Addressing it during innovation is pretty cheap usually. You just, try to simulate something, and if it fails, we can chat with you guys and try to find a solution.
That's why it's not a waterfall model, right? It's like, it's very interactive.
Yeah.
Because the design on paper, I mean, once we have this mathematical model, right, then we try to prove, we design a solution, we try to prove it. And so we make a lot of, assumptions that, because it makes it simpler then to prove the design itself, like secure, but at the same time, right, engineering, there's actually a lot of similarity, right? When does it work for you and when does it work for research? For us, it works if we make reasonable assumptions that we believe are also informed by you, are kind of fine to make, but then the proof has to go through, such that, and we have to write it up, as you said, because we want to speak kind of a standard language. That's why we put in everything in the papers to show that, this is how we model it, this is the solution, this is what we want to achieve. And then we write it up such that it becomes a coherent story, and then we let it undergo peer review, such that other people can assess it, right? It's just and to increase, of course, the confidence in the result. But this is then, this is just one step. But of course, if you want at the end something that works, and it was a very nice example with the certificate size that you brought up.
Yeah, so I feel like this time around there's yet another level of strengthening the connection between our like theoretical research and the final product. As I understand it, and feel free to correct me if I'm wrong, but for example, for current Ouroboros, there was a research paper, right? And then there was an implementation done kind of based on people's understanding of the research paper. And then there were some formal proofs about it, but in fact, not necessarily about the exact thing that is in place. And this time around, our sort of way of working is that, when we have the paper, we come to you guys and we explain our ideas, and then you actually model this formally. So you kind of capture in a formal language our model, our protocol. In fact, I was witness to an hour of magic in Paris a few weeks ago, where kind of on the fly you guys wrote some kind of parser or compiler for our pseudocode to directly translate that into your formal methods, right? And then even our like pencil and paper proofs, to some extent can be verified with this.
Yeah, I think that's interesting you bring that, because that's something we didn't mention, but it's another piece of the puzzle and something that we have been pushing quite hard within IOG and in general within the Cardano community. Something that's sometimes hard for the whole community, the community as a whole, and people who are not really deep into this stuff to grasp. But I think it's really important to have this mindset about formalizing things, because when you write something on the paper and you get this whole peer review process in scientific conferences and journals and all this stuff, it's still the step that goes from this to the actual code that runs on my laptop or your laptop. It can be quite involved, and the step of formalizing the model in the language. So we are quite heavily invested in Agda those days in the company, and I think that's kind of a bet in a way, because it's still not that many companies and not that many areas are really investing heavily into formalization. But formalization is really a way to get to get from something which is an idea and a concept then written in informally, even though the word formal is a dangerous word, but there is a formal most people think there are equations, so it's formal. But for us, formal means, your equation is actually code that is verified that is machine checked. And I think that rather than formal, there is a question of, whether or not it's human checked or machine checked. And I think that getting to the point where, I think an ideal thing, and that's, it's great you mentioned that, Sandro, but it's on your first step. An ideal direction or an ideal word where we would be able to work on the ideas from a scientific point of view and research cryptographers' point of view, and on the same, in parallel, work on the formalization, so that when you get to the publication, your ideas are actually backed by a formal model which is machine checked, and maybe not fully machine checked, because the models we are working on are very, very hard. And then once you have this machine checked formal model, then you have the seed from which you can derive other models that gets you into production.
But it's also something on which we are improving, actually, because if we didn't take Peras as an example just randomly. We took Peras because we started to work on it at the innovation level before the paper was out, actually, and trying to actually shorten the cycle time to go from innovation to implementation by taking the innovation step as soon as possible, so that we can also provide you a feedback before the paper was out, and trying to really shorten the iteration time to go through the whole process. So that's also something that is very interesting in my view, in the way we are evolving within IO.
Exactly, and the question is, what is innovation, right? And innovation, or what is innovation about? It's probably about producing artifacts that are just they increase the confidence into that what is proposed will eventually run in production, right? And of course, as you said, a research paper is pretty far away from the final production-ready system. So how do you get there? And so this is innovation. It's about artifacts that show simulations, formalizations. They show it under, in basically the lab, under lab circumstances, but also, simulations or even prototypes in kind of the environment we would expect, that they measure statistics, how it is. So backed by research papers, kind of this entire package is kind of innovation, right? Taking an idea, a problem statement, and have a trace of results that are just useful for ending up in a production-ready system.